Hey guys, welcome to our water quality project here. Normally we start out this project with a few field trips to the stream. So of course we can't do that this year. We're going to go out and we already went out for you and recorded some stuff. So we're gonna share those links with you here momentarily. All right, so for this project, we're going to be exploring water quality, particularly with regard to how we view it in the context of the Clean Water Act and the Safe Drinking Water Act of 1972 and 1974, respectively, two pieces of legislation we still use to measure water quality. So let's look a little bit at the parameters and characterization of water quality, or how we characterize it. So first, it's important to note that in terms of the Earth, fresh water on Earth, the water we have access to is a tiny, tiny little small amount of what the actual total water on the planet is. Of course, Earth is a water planet. Most of it is locked up in salt water. So oceans make up 96.5% of the Earth's water, and fresh water is 2.5%. Of that, most of it is groundwater. Most of it is glacier and ice caps, and then, of course, groundwater, and then fresh and surface water. And of the fresh and surface water, we're talking about a lot of that being locked up as well in ice, but then also, of course, lakes, rivers, streams, and things of that nature. So what we're looking at when we look at rivers and streams is 0.49% of all the Earth's water. And so it's not very much, and that's important to remember. But that small amount, along with this groundwater, are what we have available to us for drinking. And if we don't take good care of those resources, not only do the ecosystem suffer, but we suffer. Human health suffers. And of course, the larger the population becomes, the more demand there is on these resources, the more difficult it is to stay within boundaries that keep the planet and local and regional environments healthy. So this was a big problem up until the late 19th, big problem, I should say, up until the late 1960s. It's been a big problem since then as well. I'm from Cleveland originally, and in 1969, the Cuyahoga River, the main river that flows through town, famously caught on fire. You couldn't catch a fish in that river at that point. People knew that. People knew it was polluted, but to see a river burn was something else. And so Cleveland got the nickname, the city by the river that burned, for a good reason. Now, of course, I remember growing up there, steel mills and everything else. It was a very different thing to drive up the highway and see smokestacks belching out fire as they try to burn off the volatiles coming out of the byproducts of production of various things. But to see this must have been something. But it's still a problem today. We have single-use plastics. That's one of the biggest issues today. Here's a man in India shoveling materials that had just washed up on the side. And of course, last year, straws got a really bad rap for good reason. And you can still buy an MRGS metal straw if you want to. We have a bunch of them here. But the accumulation of single-use plastic is a really big problem. Now, these aren't chemical pollutions, but you do get essentially that are just as bad, microplastics. And these become incorporated into tissues, bodily tissues, and can cause other problems we don't even know about yet. But so it's a big problem. So these are physical constituents that pollute as well as the chemical ones. So here's, of course, another source of pollution are nutrients. And nutrients, we've got industrial chemicals, we've got plastics and solid items, and now we've got nutrients. And nutrients are the result or the reason why you have this red tide off of the coast of Florida. And these show up occasionally off the Florida coast. You got lots of citrus groves out to the east, overland here, and they're heavily fertilized. Of course, we had a big bloom in Lake Erie as well. But this kind of thing happens, and nutrients go out into the water body. And then, of course, the algae take off with the nitrogen, the nitrates, and so forth. And when the algae dies, the bacteria that decompose the algae use up all the oxygen that's in the body of water. We call that eutrophication. And in this case, the red tides are deadly for other reasons. But again, these are nutrient pollutions. These are anthropogenic, like the other two examples I've shown you, but they are the result of a different set of pollution related to agriculture. And of course, anoxia or eutrophication leads to fish kills. This is a really dramatic one down in Brazil, but you can see through this diagram, and you can pause here to take a look at it, the things that result from these fish kills or from these nutrient loading events. And of course, in addition to nutrient loading, we've got bacteria. We haven't even talked about that yet. Bacteria is another contaminant that you can have in surface water and in groundwater. In your senior year, we'll read the book The Ghost Map, where we learn about the cholera epidemic in London in the 1850s. But we're dealing with a pandemic now with a virus, but this is waterborne disease, and cholera is still a problem all over the world. It's native to Asia, but it's spread around the world and pretty much and exists pretty much everywhere at this point. But it does some nasty things to your digestive system and to your cells. Now you can live through it. You can live through it with antibiotics and just drinking lots of water. Eventually, your body will recover. But it's in the meantime, pretty horrible thing. This is from Yemen, from a couple of years ago when there was as a result of the civil war, a big cholera outbreak. And of course, pollution coming from what we might call natural sources. Now you can have sedimentation. You can see the difference in color in the water here. This water here is full of sediment. This water is not. Same with up here. This water is full of sediment. This water is not. And the problem here is that, of course, this sediment clouds the water and affects the ability of life forms to live in it. And this sediment could be natural. It could be anthropogenic. And so these kinds of things are common after storm events, or it could just be that there's deforestation going on up the road and soil erosion into the waterways. And of course, other chemical pollutions. This is a really dramatic pollution event in Romania in a freshwater body. The constituents we look at for water quality tend to come in several forms: dissolved, suspended, and then we have to dissolved or suspended, and then we have to measure them. And dissolved components include things like the solids that are dissolved, salts and things of that nature, various ions and cations, and then the hardness of the water, which is really a measure of the carbonate compound constituents. The suspended component we measure as turbidity, and then of course biological components, things like bacteria, diatoms. Diatoms are a form of algae, but they're naturally occurring, and their prevalence or lack thereof can be a water quality indicator. And of course, we can also talk about benthic macroinvertebrates, things of that nature that also indicate something about water quality. We measure these things with electronic probes, field chemical tests. We can bring the water samples back and use spectrophotometry, and we can just use the color of the water to tell us something about its quality. Now, with regard to the Safe Drinking Water Act and Clean Water Act, there's some important terms that are worth keeping in mind. With the Clean Water Act, it only regulates navigable waterways. So the Shenandoah River counts as navigable, but Mill Creek may not, or Holman's Creek may not. Navigable is an interesting word. How do you define that? Well, they define it in the Clean Water Act. During the Obama administration, there was an effort to extend the Clean Water Act's regulations to every single body of fresh water under the Clean Water Rule, which was enacted back in 2015, enacted by executive order, not by Congress. It was rolled back in 2017, one of the first things the Trump administration rolled back. The goal of the Clean Water Rule was to be able to monitor water quality in wetlands and other places that were headwaters. And one of the big impetuses for that was, of course, is things like in West Virginia, where they have mountaintop removal coal mining going on, where they're just you take the overburden off of the coal seam and you dump it down the side of the mountain, and it ends up in the headwaters of the stream, not only as a sediment pollution, but chemical pollution and so forth. There's a lot of concern over that, understandably. So the Clean Water Rule would have regulated all of that, but that no longer exists. Still, with the Clean Water Act, we look at the constituents' total maximum daily load, or TMDL standard. So there's some standards for TMDL under the Clean Water Act that you cannot exceed. And where they measure these things, whether municipalities or other places are measuring them, they have to keep track of them. Under the Safe Drinking Water Act, we use the term MCL, or maximum contaminant levels. These are primary and secondary contaminants. Primary contaminants include things like nitrates, phosphates, and so forth. Secondary include things like iron, fluoride. Fluorides are primary. Iron, and other metals and things of that nature. Things that aren't harmful to human health, but maybe affect the aesthetic quality of the water. And so it's important to regulate these things as well, because this is the water we consume, that we as humans consume, whereas the Clean Water Act is thinking more about primary ecosystem context. The Safe Drinking Water Act is focused on human consumption. All of these measure water quality parameters with various units. One of the most common for chemical constituents or dissolved constituents is parts per million, or ppm. ppm is like 1 part per million parts. So sometimes you see this in recipes. So 1 part chemical to 1 million parts water is 1 ppm. It's also equivalent to milligrams per liter. That's 1 part of an object to a million grams of liter, or milligram to 1,000 grams of water. So they're equivalent units anyway. Now, a good case study locally here that does affect us throughout the entire watershed of the Shenandoah River, of course, primarily the South Fork. DuPont, the story of DuPont in Waynesboro. The facility is all the way down here in Waynesboro, and they had dumped mercury in the soil. That mercury had made its way into the Shenandoah River, and that, of course, the Shenandoah River flows to the north, and had affected fish kills all along the river. And so you could detect mercury all the way up to Front Royal, where the South Fork meets the North Fork of the Shenandoah, which flows through areas right near the school here at Triplet at MRGS. And eventually, this combined Shenandoah River empties into the Potomac River. Okay, so in 1978, we discovered that this was happening. It took 20 years for them of dumping before anybody took notice and had a problem with it. And then 1978 to just last year, a settlement was finally reached. Okay, that's a lot of years. It's a $42 million settlement that's going to do some work in cleaning up, but along that stretch. But the damage has been done for a long time. And so the challenge with regulation isn't so much that the spirit of the law is excellent. The problem is that the legal processes and the regulatory processes do take time, and that time becomes a factor in the health of the ecosystem and in the health of humans, and can actually be a problem. So that's one of the shortcomings of some of this regulatory framework, is just how long it takes because of the legal system. Avtex Fibers is another example of a case study, this time in the Front Royal area. It's a Superfund site, which under the Superfund law, which is a sort of a corollary to these other environmental laws passed in the early 70s, that gave the government the federal government the responsibility of cleaning up major pollution sites around the country. And Avtex was one of those. They manufactured rayon and other synthetic fibers there. Had a long list of heavy metals and other contaminants that were dumped there. And of course, the Shenandoah River was the victim here. Now, this site's now been redeveloped. It's basically coming to the end of its Superfund redevelopment, and to apartments and parks and things of that nature. But its history is a lot less positive. And here's one of the buildings being imploded during the cleaning up of the site. So one thing you can think about is when you change your oil in the car, or you dump a chemical or whatever, is think about your watershed address and where you're dumping that chemical and where it's going to end up. For instance, if you live in Newmarket, you live in the Smith Creek watershed. That Smith Creek watershed, every drop of water that's in that watershed, whether it flows overland as a part of the hydrologic cycle, infiltrates into the groundwater system, and then makes its way through there, taking a lot more time to do it usually, as a part of the North Fork of the Shenandoah River watershed. That's a part of the Shenandoah River watershed, which is the larger Shenandoah River watershed that includes the South Fork as well, and also the areas north of Front Royal, and then the Potomac, the Chesapeake Bay, and eventually the Atlantic Ocean. So you can think of this the same way you think of your own address. You live in the United States, you live in Virginia, you live in a particular county in a particular locality, and so forth. So the North Fork of the Shenandoah and Smith Creeks, you can see the North Fork is this larger watershed of 913 square kilometers, and Smith Creek is 235 square kilometers. Smith Creek, as you can see here, is a part of the North Fork watershed. This is actually looking at just south of Mount Jackson. The Smith Creek watershed is over here. But if I would have placed this little indicator, this is at Model My Watershed. If I had placed this little indicator up here, it would have included the Smith Creek watershed as well. But for many of you, the North Fork watershed is from south of Mount Jackson, is where you're living, and for a few of you are over here as well. But yeah, a watershed is really any region within a certain elevation boundaries that drains into a particular waterway. And there's different orders of streams. There's first order streams, second order streams, and so forth. The first order streams are the main trunks, second order, and then third order as you get further out. All right, so this was a group activity at one point, but when you think about pollution, two questions to ask yourself. Is it natural? Is it anthropogenic or human induced? And then on top of that, can you identify a particular point? I dumped a barrel and it's spreading from that location. That's point source. Or is it agricultural runoff, where you can identify, maybe you can identify a particular field, maybe you can't identify a field at all, it's just coming from the region. So pollution can have be natural or human, it can also be point source or non-point source. Other indicators of stream health include things like sediment, microbes, algae, mollusks, fish, and so forth. You don't think of sediment typically as a pollutant, but the smaller fractions can certainly be a pollutant. Sediment comes in a variety of sizes and compositions. Diatoms are single-celled algae or protists that will tend to thrive or not thrive depending on the quality of the water, so they can be good indicators of water quality. They are also primary producers, so they're the base of the food chain. Other things eat these things, and if they're not present, then those other things that eat them aren't going to be present either. They also produce estimates suggest they produce up to 50% of the oxygen we breathe. Let that sink in for a moment. So when stream water quality, surface water quality is not in optimum health, that is affecting how well we can breathe. So we are directly affected by water quality in ways that, we don't even have to drink the water. We can just be thinking about how we breathe. All right. And of course, diatoms are really cool. They have a particular structure, like any organism. They have valves and so forth. Mollusks, freshwater mollusks, are also another good indicator of water quality. Some people call them bivalves. There's also gastropods or snails. Up to 50% of all Virginia water mollusks have been extinct or are extinct already or endangered. And their life cycle is dependent upon other organisms and the quality of the water, including the other fish that are around. So they're very sensitive to water quality. If you go to the streams, you'll see plenty of bivalves, but only certain ones. Other bivalves may no longer be there. And these are not really all that well studied here in Virginia. At least our local ones aren't. And of course, they have their own anatomy as well, and they are evolved to live within certain ecosystem niches. And of course, snails or gastropods can live under the water, depending on the species, underwater or on land. And the same with these bivalves. Generally, they're all underwater, but they have different life modes. So they might sit on the surface, or they might burrow into the ground. Some, like this freshwater mollusk, will be a mature adult living in the sediment, the substrate. Will expel an egg, which then will then make its way through the water column, and within 10 days become a juvenile. Some of them have to encrust onto particular fish hosts, in this case a minnow. And then by spring of the next year, you finally have the juveniles being reimplanted into the sediment. So because of this, we have a mutualism or a coevolution that's gone on within these ecosystems. If you have eutrophic conditions and the fish die, then this mollusk is going to die as well, because you can no longer have this mollusk um, complete its life cycle without that fish being present. So water quality is important, and the system exists in a state of dynamic equilibrium like any Earth system. And when you throw that system out of balance by the inclusion of a chemical pollutant, or that you take away oxygen, you're going to affect the entire ecosystem. It's important to remember that as we think about water quality. All right, that brings us to an end of this, and hope you enjoyed it, and hopefully it was helpful. If you have questions, let me know.